what I'm going to do is, of course, this is a tremendously vast area of study. I mean, lambda CDM happens to be our paradigm of understanding of cosmological evolution, but the number of models that exist in against or alternative to lambda CDM are as diverse as probably as many cosmologists around in the world. So it's a huge area. So what I'm going to do in this short summary, in some sense, would be to first introduce you to the basics of cosmology. So just set up the stage using the lambda CDM model, and then use two toy models, roughly. One that would be sort of looking at the dark energy sector, and another model looking at the dark matter sector. And then the idea would be how these models finally imprint in this utopian future when 21 centimeter signal would be detected. So we know that it's tough and we are far away from it, but and that's why we would be very much into future in some sense. We'll talk a little bit about the observational issues, but not much, because the idea would be that if we do get the signal at some point of time, then how do cosmological imprints sort of manifest itself in the signal? So that's the outline. So I'll just go quickly through basic cosmology. So Tirth yesterday gave a very beautiful overview. So this is first we talk about the homogeneous and isotropic universe, which is the picture that we have of the universe on the largest scales, on scales larger than typically 100 megaparsecs. If you smooth the universe, then you know it's homogeneous and isotropic. And Hubble's law, which is the expansion law, which is consistent with homogeneous and isotropic universe. And then, of course, we have the composition of the universe on which is radiation, thermal radiation, microwave background at 2.7 Kelvin, baryonic matter, dark matter, and dark energy. So as you can see that the dominant part of the universe is the energy budget is dark matter and dark energy, constituting almost 95%. And then you have known matter, which is mostly hydrogen, as Kanan just pointed out, and that's a very small fraction. So interestingly, the idea is that we can only observe this baryonic matter. In fact, we'll see how to observe this hydrogen. And then the imprint of the rest of these two, which we don't know, dark matter and dark energy, is supposed to manifest in whatever we can observe, which is the baryonic matter. All right, so the lambda CDM model is the standard paradigm. In lambda CDM model, the dark energy sector is believed to be the cosmological constant. The cosmological constant which appears in Einstein's field equations. It's dark energy, which has an energy momentum relation with an equation of state exactly equals to -1. So the pressure density relation has an equation of state parameter -1. And the dark energy doesn't cluster and it's non-interacting. And then in the dark matter sector, we have what is called cold dark matter, which is again something which has no interaction other than gravitational interaction. And it's stable, it doesn't decay, and it doesn't couple to anything else. And it's cold, so there is no pressure. So this pressureless fluid is what we have called the cold dark matter, and then this dark energy. So this is the standard model of the lambda CDM universe. And so what we can do is in this standard model, we have the expansion history, which is given by just one quantity, which is the scale factor, which is telling you how the universe is expanding. Of course, there is another thing which could play an important role, which is the spatial curvature. But from several observations, we are now more or less certain that the universe is spatially flat. So in a spatially flat universe, the expansion rate is just governed by just this, knowing this one quantity A suffices, and it's given by this equation. So as you can see, you have this cosmological constant which sits over here. There is no dynamics in it. There is no Z dependency. There is radiation and matter. And idea would be to now measure this expansion history. And if you just look at background cosmological evolution, then the quantity, if you go back to even Hubble's original plan of looking at cosmological expansion, you were looking at distant objects and galaxies, and you were typically measuring distance and expansion rate, right? That's what people were trying to do. So in the same way, typically when you are just looking at the expansion history with the background cosmology at mind and not looking at structures, then you would typically be interested in measuring distances to distant objects and the cosmological distances, and measuring the rate of expansion at very large distances. So typically this pair of two things are of interest to us, and that will be important for us as we go along. So to measure this distance, we know that either we can have what are called standard candles, so objects which have known luminosity, and if you measure their apparent magnitude from your observation point, then you can measure the distance using the standard candle from the known luminosity. The other things are what are called standard rulers. So here you have a standard length, something whose length you know, a length scale which is known precisely to you, and then observing what that length appears to you in angular scale. So as an angle subtended at your vantage point, you make predictions of the distance. So this is the angular diameter distance and luminosity distance, and which are typically measured. Now, what I'm going to talk about, angular diameter distance, because this shall be important for us. Now, if you look at this expression for angular diameter distance for a flat cosmology, it's just given by this integral over z. And instead of writing in this integral form, you can actually define a quantity which is the scaled angular diameter distance. As you can see, we have just divided by c by h naught. And then I can look at the derivative of this x, which is dx dz with respect to redshift. And then you can see there's a nice relationship between this x and a p. It's like if you look at this in this plot, x and p, which you can think of as a phase space, because x and its derivative constitutes a phase space. In this phase space, you can see this is for a given z. If you fix the value of z, then this is a straight line with a y-intercept which is constrained by the value of h of z. In fact, this is what is called the E of z, the inverse of h of z. So for a fixed z, you have a straight line. Now, you can look, if you put z equals to 0, then you have this line. And if you have different values of z, you can get all these straight lines with a y-intercept, which is given by something which depends only on h of z. So this relationship is a kinematic relationship. It's a definition, basically, right? It follows from the basic definition of the angular diameter distance. So it's a constraint relation between x and its derivative. So the angular diameter distance and its derivative. But this is not going to tell you much because we don't know h of z. So if you know z and you know the value of h of z, then you can get this line. But the question is, what is the value of this phase point? Which means, where is this phase point located? To do that, we actually now need to know the dynamics of the universe. So I can write my Friedmann equations, the expansion history which I wrote, in this following way, in this very interesting way. You can define, as I just did, x to be the angular diameter distance, p to be its derivative. Then I need an equation of motion, just like you have in mechanics, Hamilton's equations. I need an equation of motion for p, and I write it in this form. So p prime is some f. Now, if you go back to your definition of p prime would involve a derivative with respect to h. And if you know h of z as a function of z, so you know what the expansion history looks like, you can actually calculate it and you will get this f involving this e. E is h naught by h. It's a nice sort of a force term. Clearly, you can see that you need to find the derivative of the Hubble expansion rate to finally get the distance and its derivative. Please understand that the derivative of the distance has the information of the Hubble. So you have a distance x and its derivative p, and the derivative p is sensitive to h. So the distance Hubble pair can be sort of thought of as a xp variable in some sense. So you can calculate this if you know this e prime. Now, if you know this e, Well, if you knew this E fully, if you knew everything about the expansion history, then you knew what this is going to be, and then you have constrained the expansion history in the phase space. So that's X and P. Now, unfortunately, you don't know this because this sector, well, you know something about the matter, that it falls off as 1 by a cube. You know something about the radiation sector, but you really don't know anything about this. And the dark energy sector is something which, well, for lambda CDM, you know what this is, but in generally, you have no idea. So this is where you put your dark energy models, and it would imprint on your E, and E prime will affect your F. It will come here, and you get your phase space. So this I have calculated. So if you can write the dark energy in terms of equation of state parameter, so you just define W of Z as this ratio of P by rho, assuming that the dark energy is a fluid, then for that particular kind of parameterization, it's not necessarily true that you can do this, but if you can express the dark energy by an effective equation of state parameter, then this E prime will be given by some expression, and you can then just find this F, which you can use now to solve your dynamics in the XP phase space. Now, for example, we know that for lambda CDM model, this is -1, and then this term simplifies quite a lot. But then, of course, you have models where, for example, this is a very popular parameterization of your expansion history, where the dark energy equation of state is given by 2 parameters, W0 and W1. As you can see that at very large redshifts, when Z goes to almost very large values, you can ignore this one, and it just becomes W0 plus W1. So it effectively becomes a constant at very large redshifts. And at very low redshifts, when Z is close to 0, it becomes W0. So it's like a dynamical equation of state, which varies from W0 plus W1 at high redshifts to its value W0 at low redshifts. So it's some evolution of dark energy in some sense. It's a very popular parameterization. And then, of course, there is this entire industry of working with dark energy as originated from some scalar field theory, where you can have a scalar field, and you can write an equation of motion, which is the pressure of the scalar fields. If it has a potential V of phi, then this is the pressure, and this is the energy density, which follows from the energy momentum tensor. And then you can show, clearly you can see this W phi, if this phi dot is much, much smaller than this potential, which means that the potential is so shallow that the phi dot is actually close to 0, then you can see that this is effectively, if you brute force just ignore the first term, this W phi just becomes -1. You can just throw away the phi dot square. But of course, you can't quite throw it off. That just would mean it's basically cosmological constant. But well, if you can use this condition that, okay, well, it's not maybe so small that I can throw it away completely, but if you take these conditions that phi dot square is much, much less than V phi, which is what is called the slow roll condition, and of course, you have the equation of motion for the field, again, use this, then you can effectively show, just using these Friedmann equations and the equation of motion for the field, you can show that there's an effective W phi can be written as -1 plus something, small term, which is related to basically the shape of the potential. So this is what is a takeaway. I mean, if you don't understand this, it's not so important. What I want to say is that if you have a scalar field, it turns out that you can construct scalar field with potentials such that you can adjust the shape of the potential in such a way that you can effectively get a equation of state, which is very close to -1, close to lambda CDM with some corrections, which will be sensitive to the shape of the potential. Okay. So here is the picture that I was talking about. So here is X and P. Remember, X was the angular diameter distance scaled. P is the derivative of the angular diameter distance. These dotted lines corresponds to the consistency relationship, so at different Zs. And these different trajectories corresponds to a whole set of models where, as you can see, the intersection of the curves with the dotted blue lines would actually give you the value of X and P at that redshift. So that's an interesting, I mean, it's just plotting position, the angular diameter distance and Hubble in a plane. But instead of plotting the Hubble h of z on the y-axis, we just plot the P because it has a nice physical interpretation of being a being a phase space. This is a XP kind of phase space. So as you can see, all these models, this is Z equals to 0. So over here, they all start here. And this is the present epoch, and this is Big Bang. So all of them have to go there. And in the middle, you can see different models. They have differences. So this is lambda CDM, which is in the red. The CPL parameterization, which I saw, I mean, there are different models. I mean, this SPF is a certain model where we have the H of Z parameterized in a certain way where you just parameterize the scale factors evolution using some parameters. And then this TQ is this model where we have some potential and we have a slow rolling of the field. So, I mean, so you can see they're all over here. So the idea would be now, I mean, well, there's lambda CDM, of course. Now, and this is just a small, obviously nothing exhaustive about this list, a very small number of possible problems, models which you can do this. There are incredibly large number of models. So the idea would be to use this kind of a picture, this position, which is in this case the angular diameter distance, and the Hubble to rule out models. So the idea would be to observationally rule out models at different redshifts. So I can make observations at different redshifts, and then I will actually measure this X and P, and I will be able to eliminate models. So that's the idea. So much about background evolution. And now let's talk about a bit about structure formation. So I'll just quickly go through. So we know that there were tiny fluctuations at around 1000, which grew out of gravitational instability to form the structures that we know now. So we will assume that at least in the lambda CDM, this is just cosmological constant, so dark energy is non-clustering. So you have this overdensity field, which is of interest to us. And in the linear theory, we split this in a spatial part and what is called the growing mode of density fluctuations. So the spatial part is believed to be a random field, maybe generated by some Gaussian process. And this is d of Z, which is which tells us how these fluctuations grow in time. And then you have these linearized fluid equations and Poisson equation, which can be solved and combined in this. And when Teal's talk you saw yesterday that finally this density fluctuations satisfy this equation where there is Hubble damping, which is like a damping term in an oscillator problem is proportional to delta dot with the Hubble appearing as the damping constant. And then you have competition between pressure and gravity. So if you just don't have gravity and have pressure, you can see this is an oscillator. But if you have gravity, then there's an exponential solution, which leads to possible growth of fluctuations. So for this equation, which is the combination of these equations, you combine them. And then the idea is to find solutions of these equations which are increasing in time. Now, for our interest, we would be considering this quantity called the logarithmic growth rate. So if you just look at this d, which is the growing mode of density fluctuations, you take its derivative with respect to log of the scale factor. This is very crucial. I mean, you might be asking that why this rate of growth is important. It's important for various reasons, but it's particularly important because if you look at the velocity perturbations, for example, if you have peculiar velocity, so any velocity which is not Hubble flow, Hubble velocity and anything departure from that, if you have a peculiar velocity field and it's say curl free, then you can write it in terms of a velocity potential. And if you use the fluid equations, you can show that this velocity potential is actually related to the overdensity field and this f of a. So basically, if there is overdensity and peculiar velocities are generated by nothing else but just this overdensity, then you have this nice Poisson equation, and over here this f of a appears. So this f of a is important because it incorporates the effect of peculiar velocity, provided the peculiar velocities are generated by overdensity delta. Okay. So, of course, as I said, that the spatial part of this fluctuations, they form a random field. So typically we are interested in different statistics, for example, the correlation function where you take these at 2 points and take the expectation value. These expectation values are to be taken over arbitrary large number of realizations of the field. But typically we believe that we can replace this ensemble average, which you would actually be needing to calculate this expectation value for different realizations, by just taking this average at different parts of the density field. So you can use what is called ergodicity and just calculate this expectation value as a volume average instead of what is called averaging over ensembles. And then, of course, we also assume to a large degree that there is statistical homogeneity and isotropy, which means these statistical quantities, they are not different along any specific direction, and they are also the same at different places of the field. So you can make all those assumptions. And then it's also convenient to work in Fourier space. So you can go to the Fourier space, and then again, I just wanted to bring this velocity thing back, because as you can see in Fourier space, it's interesting because you can write this again as this f times delta. So this is important because this velocity vector has this k vector in the numerator along with this. So this will become important for us later. Okay, so this is the power spectrum, which we talked about yesterday. This is the whole dark matter power spectrum. And you can see the large number of observations that are actually constraining the power spectrum over here. So this is over here, you have basically, these are mostly from CMBR observations and all large scale structure, Lyman alpha forest here, and galaxies, etc., constraining the power spectrum. Okay. So another thing that's going to be of interest to us would be this quantity called sigma r. Now, what this quantity is, it's basically that you have a density field. So if you have a density field delta r, what you do is you smooth this density field. So you say take a filter of radius r, and this you call the smooth density field. So what you have done is you have put a sphere of size r and sort of averaged it within that sphere. And then this quantity sigma r square is basically this variance of this quantity. So that you can compute by going to the Fourier space, and then it turns out to be related to these window functions of an integral over the power spectrum. It's a very important quantity in cosmology because the value of this allows us to normalize the power spectrum. It can be measured, and it allows us to normalize the power spectrum. It's also interesting to note that if you have this correlation function, remember the correlation function gave us this the correlation between the density over density field at 2 points. Now, if this xi of r, so it depends on the separation of the 2 points. If you see it's something like this, it decays off like this, which means as you go farther and away, the correlation actually decreases. So let's say it's some function which decays off. Then you can show, and it's very interesting, you can see this if xi r goes as r to the power minus n, I mean just a toy model, then you can compute this sigma r square, which will go as 1 by capital R to the power n with the growing mode and just follows from this this power spectrum. So the power spectrum you can just put from the xi of r, and then you can compute this xi. It will go typically as 1 over r to the power n with the d plus square, which essentially means that if there is a radius r at which, if you smooth, so you keep increasing the radius, maybe there is some radius over which this sigma square r approaches this value unity, well, order of unity. Now, the moment it appears to reach this value unity, then that overdense region becomes what is called weakly nonlinear, because there's a lot of overdensity there, and a collapsed object forms. So typically, collapsed objects of size r forms when this guy, sigma square r, approaches unity, okay? Now, if you put that condition over here, and if you solve for this growing mode, say in the matter-dominated epoch, which goes as 1 by 1 plus z, then you can immediately see this r will go in this way. So the size of that object will have a scaling which will go as 1 plus z to the power minus 2 by n. So and which essentially means that larger the value of z, the smaller the value of r, which is the statement of what we call hierarchical structure formation, which means that at large redshifts, which means at early epochs, first small objects collapsed, so r small, so smaller objects collapse first, and then larger and larger objects collapse later. So the hierarchy of structure formation happened from smaller objects collapsing first and then growing. So it follows just from the definition of the sigma r. Okay. Now, I'm just talking about things which are of interest to what we shall do. So we define something called this F sigmoid. Remember, F was the logarithmic derivative, this quantity of the growing mode. And sigmoid is related to the normalization of the power spectrum. R is 8 taken to be 8 H inverse megaparsec, which is the typical size of a cluster, a typical scale of nonlinearity. And this is the quantity which is of interest, F times sigma of 8, because F and sigma tend to have degeneracies between them in observation. So again, the equation of growing mode and the equation of f of z can be combined, and you can have an equation, a set of equations involving these, which, as you can see, again depends on the equation of state of dark energy. So what I have done is I have again written a set of equations, but now it involves quantities like f sigma 8, which is defined as this d plus, and its derivative, which is this quantity. So what I have, again, a set of equations, and you can solve this along with your x and p, and you will see now a three-dimensional plot where the z-axis is now f. So it is the growth rate of density fluctuations. So you have now x, the angular diameter distance, the derivative of the angular diameter distance, and on the z-axis you have structure formation, growth of structures, which is f. And you can see all these models tends to form this narrow band, and this is Big Bang, so they start from somewhere and they all sort of evolve and tend to this. And you can plot your favorite model. What you need is what is the dark energy equation of state, and you can solve these equations and get to this picture. Again, as I said, if you have data on clustering, if you have data on F, if you have data on angular diameter distance and Hubble, then you can constrain these models directly over here. So what is the takeaway lesson at this stage? The takeaway lesson is we need to measure the Hubble, h of z, the angular diameter distance, and the growth rate of structures. That would give us a nice way to constrain a whole bunch of possible models and exclude models from their behavior in the phase space. Okay, so lambda CDM, as we just said, is the standard paradigm, but it has many problems, theoretical problems. I mean, the value of lambda as is predicted from particle physics seems to be way off from what you observe. The measured value of omega lambda, there are observational challenges. There's this famous Hubble tension where the value of the Hubble constant measured from very local measurements like Cepheids distance measurements tend to disagree with measurements from CMBR and large distance measurements, early universe measurements. So that is a serious trouble. There's a 6 sigma departure of the values of H naught. H naught measured from Cepheid variables turns out to be around 72, 73. It turns out to be 67 point something from CMBR. So that is a big challenge. And there's a big, nice review as you can look at this review. It's an excellent review. It talks about innumerable attempts to solve this Hubble tension by invoking all sorts of models in the dark energy sector and the dark matter sector. So people tried out scalar fields, modifying the gravity. Maybe Einstein's theory is wrong, modifying gravity, interacting dark energy, decaying dark energy, dark matter interacting, and you have scalar field models. And in the dark matter sector, you have decaying dark matter, you have warm dark matter, dark energy, which did not start late in the universe, but started showing up early on, large non-Gaussianities, and everything that you believe in your standard cosmology. If you can just let it go, you can try to sort of fit with these observational tensions. So then, I mean, all these have been attempted. This review, you can take a look. It's a, I mean, very nice review. Okay. So now what we are going to do in this particular workshop is to focus on one observational probe, which is studying the neutral hydrogen distribution. And Kannan gave a nice talk, so I'm going to go through this very quickly. So the transition we are looking at it is a 21 centimeter transition between these hyperfine levels. And as you saw, that the quantity that we are interested in is this, the difference between the spin temperature against the CMBR temperature. And that you can see is proportional to the optical depth. So this is the picture of what's really happening. So redshift 1000 is where decoupling happened. So the universe became neutral, as you can see. And then as you have a whole regime where the universe is neutral, then at some stage around z equals to 20, the first stars would try to form, and they would form and try to ionize the universe, and then universe, these ionized bubbles form, universe gets mostly ionized around redshift 6, and then you are left with in the present universe, which is mostly ionized, with these small clumps of neutral hydrogen, which are self-shielded, and they are located probably in what are called damped Lyman alpha or galaxies. So you have absolutely neutral, and so you had, of course, previously before the CMBR decoupling happened, you had ionized universe, then proton and electron combined to form neutral hydrogen, the decoupling happened, the photons started free streaming, the mean free path of the photon became close to the Hubble radius at that epoch, and then you have neutral hydrogen. And we also have marked this redshift 200 because, as Kannan pointed out, it's only between this redshift 220 that, due to the departure of the spin temperature of the 21 centimeter transition from the CMBR, that we would be able to detect it. Because before 200, from 1000 to 200, due to coupling, the spin temperature, so if I look at this slide, you see over here in this regime, the spin temperature couples to the CMBR temperatures, so you can't quite see it. It's only when the spin temperature departs from the CMBR temperature that you can see it as either emission or absorption feature on top of the CMBR. So, and that happens only after z equals to approximately 200. So from 200 to 20, you see, as you can see this in absorption because the spin temperature is below the CMBR temperature, and then due to heating, the spin temperature rises, and you start seeing the 21 centimeter in emission. So as Kannan mentioned, we are looking at radiative transfer of photons traveling from the large scattering surface to us through an intervening gas cloud. And this is the differential brightness temperature. What is important for us is that it's sensitive to this quantity called tau. Kannan did this derivation, so I won't go through it again. So it's related to this absorption coefficient, which is given by this. What is important is to note is that we have this line profile function, which leads to this quantity del R del nu, which is the R is the co-moving distance to the source, and nu is the redshift in units of frequency at that source. So this is important because this R that we observe is never measured in real space. So how do we measure distance? We always see light and we measure redshift. So what is measured is always redshift, and from redshift, we infer a distance using some cosmology. So the idea is you measure redshift to a source, and you, from that redshift, you use some cosmological modeling to get a distance. Now, this would imply that the redshift was entirely cosmological. If the redshift was entirely cosmological, then it would be converted, its conversion to a distance would be accurate and the distance would be correct. But if, apart from the cosmological redshift, if there's some other anomalous redshift, something non-cosmological, for example, if you have an overdense region and there is a peculiar velocity around that overdense region, then the peculiar velocity will give rise to something which is a departure from the Hubble redshift. So you'll get a V by C where V is a non-Hubble velocity. So what you would have is that the redshift space, the distance which you measure, and the actual co-moving distance, they would be off. They would be differing by this redshift. Now, what this does is that since you are now looking at distances measured purely based on cosmology, and you don't know that there is a part of that redshift which is coming from peculiar velocities or something like that, it would lead to a distortion because, and that is what is called a redshift space distortion. So as you can see, this del R del U actually will have, I mean, you have R, which is nice, but you have this del Z del R. So this Z is relating to this V by C, some anomalous redshift coming from peculiar velocity. So you would have a contribution, which is this dV dr, and where V is a peculiar velocity, and all these are converted to standard things. And if you remember, and this is why we had written this expression for V very early on. So if you go back, so this V, okay, here. So this V in Fourier space, as you can see, is related to this is k vector and proportional to delta with this f. So what will happen is when you look at this quantity here, this tau, this dV dr, this when you take a Fourier transform, it will be something which is going to be proportional to delta of k. So that's the important part. This peculiar velocity field over here leads to something which is proportional to the density field over here. So this is the general formula, and then we will look for cosmological reasons and dark energy because we are interested in dark energy at low redshifts less than 6. And at those low redshifts where dark energy is supposed to manifest, we immediately can drop out a lot of these terms because the spin temperature, as we saw, is much, much higher than this CMB temperature. So wherever you have a spin temperature Ts, for example, you can use, for example, in this formula over here, and you can take this Ts out of the, and T gamma by Ts you can drop. So what that does is simplifies our results drastically, and what you have is the differential brightness temperature to be just something which is this normalization which depends on redshift, and it's proportional to the fluctuations of, now here we are looking at fluctuations. Remember this tau can be expressed. Tau is proportional to rho, and rho, if you can write it as a rho bar and times 1 plus delta, then tau will be proportional to delta, and delta tau will be proportional to delta, and then delta TB will be proportional to delta. So as you can see, this all this becomes basically proportional to fluctuations of the H1 density field and this peculiar velocity. So this is what you have. So we are going to look at this post-reionization epoch where the spin temperature is much higher than the CMBR temperature. So 21 centimeter radiation is seen in emission. The neutral fraction, which is the most important thing to understand when it comes to the epoch of reionization, remains approximately a constant, mostly a constant, so we don't have to worry about XH1. The peculiar velocities will be determined by the dark matter distribution, as I just mentioned. So peculiar velocity will manifest as redshift space distortion and anisotropy. The gas is housed in what are called damped Lyman alpha clouds. So they are clumped clouds which are self-shielded, and and we are not going to be interested in sort of looking at individual sources, but look at some sort of a diffuse collective emission coming from all these different sources. The processes underlying these fluctuations would be believed to be Gaussian, and most importantly, we have to now understand, if I have a density field, which is dark matter density field, how is the gas distributed? So we have said that these gas are in the post-reionization epoch, they are in these halos, in these damped Lyman alpha clouds, but exactly how are they distributed? And that distribution would lead to a relationship between the underlying dark matter field and the H1 field through a bias function. So this is from simulations. So if you simulate the cold dark matter field and then identify collapsed objects and halos, and you populate the halos with neutral hydrogen, and then you compute the power spectrum of the neutral hydrogen and the power spectrum of the dark matter. You see they're off, and that ratio is given by the bias. And this bias is now shown here as a function of K and redshift. It depends on both redshift and scale, but as you can see that this remains largely constant over a very large range of K modes. So it's on large scales, it is pretty much constant. And at small scales, obviously, the bias tends to rise. So this bias function is what is the important governing quantity which will dictate the 21 centimeter power spectrum in the post-reionization epoch. So the expression which I had written over here, so this quantity, if you go to Fourier space and convert everything, this will become delta. This is just Z dependent. This dVdr, you can convert it to Fourier space, and you put all that in, then this just becomes, the power spectrum becomes, and take the power spectrum. So what you have is the power spectrum of the 21 centimeter distribution essentially becomes proportional to the dark matter power spectrum through a set of quantities. Of course, this depends on the expansion history, and there is F, which is the growing mode, and the bias sitting over here. So this T bar is just dependent on H of Z. Okay, so it's what is important is that this bias and the mean neutral fraction, this is pretty much what you need to model. So it's basically a very good tracer of the dark matter power spectrum. So the 21 centimeter power spectrum in the post-reionization epoch, where we are assuming that the gas is just located in these nice halos, the power spectrum is just proportional to the dark matter power spectrum. So it's a tracer of the underlying dark matter field. So anything that you want to observe in the underlying dark matter field will manifest in the post-reionization 21 power spectrum. Specifically, for example, galaxy surveys, which galaxies are believed again to be tracers of the underlying dark matter distribution by some bias, and they also have this similar kind of redshift. This term is the redshift space distortion, and so there is this very similar relationship there as well. Okay, so a little bit about observations. So I'll just quickly go through this because what you do in radio. Okay, so we want to look at an interferometric observation. So what you measure in a radio interferometer, as you know, is this quantity called the visibility, and you have the signal and a noise. So the signal is essentially the Fourier transform of the intensity on the sky, as you can see, and this in Rayleigh-Jean's limit, it's just this brightness temperature. And there is this antenna pattern, and when you write this fully and using all the quantities of interest, and you find the correlations between the signal at two baselines, UA and UB. So if you have two antennas separated by a distance d, then the d by lambda gives you what is this called the U, the baseline in which you actually look at the Fourier transform. So this signal, the visibility correlation, that gives you basically something which is proposed. That's all that's mattered to us, that it's basically, it's an estimator of this power spectrum, and through obviously these conversions in a very simplistic, and I mean, it's much more complicated than this, but in a much quite simple approach, you can show that this visibility correlation actually gives you something which is estimator of this 21 centimeter power spectrum. And then of course you can add noise. Noise, as you can see, depends on what kind of antenna distribution you have and its various noise properties. So I won't go into the details of this, so let me skip this. This is some signal to noise. I can ignore that as well. So the point that I want to speak about a little bit is that in these observations, there is clearly one big problem that you might think that if you detect this power spectrum, which is great, because if you could detect this, it's incredible because you directly can then measure this dark matter power spectrum, and it's cosmologists' playground because you can constrain all sorts of things. Unfortunately, detecting this is tremendously problematic because of the cosmological signal, which we are interested in, is plagued by signal from our own, which is the foreground from our own galaxies in form of synchrotron radiation and other point sources. And these foregrounds are tremendously much larger in magnitude, several magnitudes larger than the actual signal. So detecting the signal is very difficult. So I won't go into those things as well, lack of time. So there are several issues. Yeah, so since I started with this XP, remember I started with X, which is dA of Z, and P, which is related to D of dA dZ. So I would be typically interested in measuring these two quantities together, and that is exactly what baryon acoustic oscillations allows us to do. And therefore, if I can measure X and P, which is this is related to H, so H and angular diameter distance, if I can measure this independently, then I can constrain cosmology. So that's what BO is all about. Now, to do that, what we are interested in BO is to measure this H and dA, obviously. But how do we do that? It's angular diameter distance, if you remember, is the distance if you have an object of some length, and then if it subtends an angle delta theta, then this d times, you have it has some distance s, say. So angular diameter distance is s times delta theta. So this is what you are typically interested in. So you need something of a standard length in the sky, and you want to measure its imprint at your observation point, the angle that it subtends, and that would allow you to measure this d of a. So what you need is something of a standard length in the sky. To measure H, you need something of a standard length, but not in the transverse direction, but in the direction of line of sight. So if you have something along the line of sight, then you know that if these 2 points have a difference by Z, then this distance would be CZ by H. So again, if I could measure the redshift over which that standard length it's sort of appearing in the line of sight direction, then I can measure this H. So this is the idea. Now, I need, therefore, it would be very nice if I have in a three-dimensional universe a way to have a length that I can measure in both transverse and longitudinal directions, and therefore measure d of a and h of z independently. Now, it turns out that indeed there is such a length scale, and that turns out to be the sound horizon at the epoch of recombination, or the epoch of decoupling. Okay, now let's just quickly go through that. So the idea is the following. So if you remember that the very early universe was hot, so the free electrons and photons were tightly coupled. So you can think of this picture in the following way, that let's see what happens to a density fluctuation as it evolves over time. So what are the things that I have? I have radiation, I have baryons, and I have dark matter. Let's say I have only these three things, okay? And let's say I'm looking at this evolution as a function of time. So let's say this is Big Bang, and this is radially outwards. So let's say I give some initial density fluctuation in all these three, some seed of perturbation. So it's some over density. So I'm plotting delta, okay? Now, what would happen is dark matter does not have any pressure. It has no velocity dispersion. So the dark matter will not move. Whereas photons, which are coupled to the baryons through the electrons, basically, through Thomson scattering, this fluid, the coupled fluid between the photons and the baryons, will have a sound speed. It will move like a fluid through this medium. So what will happen is, so you start with this, at a later stage, what will happen is this cold dark matter will stay dark matter, whereas the photon along with the baryons would have shifted. Now, this is not just going to happen. The dark matter, which is over here, now the baryons have shifted by some amount along being tightly coupled to the photons. What will lead to is that this will start spreading out because this has some potential well. So eventually this will start getting broadened because it's pulling some matter into it. Now this fluid, this is the combination of, so I have the combination of radiation and baryons, they'll keep moving. Okay. Now, it won't keep moving forever because at some stage, the temperature of the universe drops such that neutral hydrogen is formed and these electrons are no longer free and they form neutral hydrogen. So at this stage, what would happen is that, so if I drew the radiation with some other color, the radiation will start fizzing out. So at this stage, the radiation, the density will start decreasing, so it will sort of fizz out, it'll go away. It'll just basically free stream away, basically leak out. So what will happen is that this baryon peak will sort of stay there for a while. And now what happens is that there's this cold dark matter, which is already just broadened by a little bit. It'll pull some of this over here. And finally, what you would have is a picture something like this. So they will both drop. And you will have a baryon little peak over here. The photons have fizzed out. The initial overdensity region has pulled back some of the matter and it forms a distribution. So this is R. Now what will be this distance? So it is the distance up to which the coupled fluid actually could drag the baryons up to. So this is what is called RD, the sound horizon at the drag epoch. So this is about just one little peak, like one little over density field. So what it means is that what it means over here is that you have, for every peak in over density, a smaller peak of over density which is separated by RD. So it will form this ring-like structure. So if you measure the correlation function would have, like every, is going to peak by a separation of RD. So if you plot the xi of R, so it will have a peak over here. So this will be this RD. Now this is important because the moment you have the correlation function having a peak, if you go to the power spectrum, the power spectrum will start showing wiggles. And that is what is called the baryon acoustic oscillation. So this is the baryon acoustic oscillations in K. Now, so this period, the period of oscillations is the sound horizon at the decoupling epoch. And now the question is, as you can see, this oscillation sin x by x, this is the baryonic, x is this quantity. It's in 3D, so you have the sound, the S is basically this distance RD. So if I can now measure this S perpendicular and S parallel, then I have my measurement of these two quantities, dA and H of Z, which is our aim. Because I know that I can, from dA, it will manifest as a theta, and H will manifest as a Z, delta Z. So if I can locate these theta in my data, then I will be able to measure this. And that's exactly what is done. So choosing these as two parameters, you can do what is called a Fisher matrix analysis, the parameter estimation thing, and you can measure, I mean, if you don't understand it, it's okay. You can measure this dA and H of Z. So let's attempt to see what it's usually, how it's actually done. So you have some model of H. This is some model, and it has some cosmological constant and some running W of A. So it's some dark energy model. So I can skip this picture. So what is shown here are the predicted error bars on measurement of H of Z and angular diameter distance at different redshifts, which follows from this kind of a likelihood analysis based on some observations. Okay. So once you have these, you can then go back. So this is the picture that I want to show. So remember, you had this XP portrait, and you have different. So this orange ellipsis corresponds to measurements of power spectrum with SCA, and then this blue ones corresponds to measurements with galaxy surveys. So you can see each of these measurements at different redshifts. They're giving us a region in the phase space, and you have obviously these constraint lines whose width, this little blue shaded region, corresponds to errors in H of Z. Remember, the y-intercept was H of Z, related to H of Z. So observationally, as you can see, you have these regions which you can constrain, And this is combining different data sets. You see the error bar, the region has shrunk considerably. And you can see so many models. Now models are having tension with the data. For example, this model seems to be out at 3 sigma, whereas lambda CDM seems to be quite well inside. So you can choose whatever data that you want, and whatever model that you want, you can put all that information into a picture like this, and you can eliminate models. So that's how we can discriminate and choose between different models. Okay, so one last thing. So I promised I'll do a little bit of dark matter. So I'll just quickly go through this. So this was about dark energy. So dark matter in lambda CDM model is believed to be cold. So it's perfectly stable matter, doesn't decay into anything. It is no pressure, but there's no reason to believe that it's stable. So we consider, for example, a typical scenario. There are many variations of these kind of models. I'll just take a very typical one where there's a decay of this dark matter into 2 species. So I'll just, so it's some dark matter decaying into 2 species. So what happens is that the original thing was a stable dark matter, what you call cold dark matter, but it's not quite cold, because it's decaying. It has gone into a photon, a relativistic species, and something which is massive. So what happens is that these densities no longer remain the same. So you can start with your fluid equations in an expanding universe, and now this decay is governed by a quantity called gamma. So gamma is the rate, the decay rate. So 1 by gamma is typically the lifetime of the particle. And epsilon, there's another parameter called epsilon, which is the fraction of the total mass of the original particle that has gone into this daughter. This is a massless particle. So these are the two. So it's a completely phenomenological model. We don't care about what kind of dark matter it is, whether it's axionic or some sterile neutrino. So people try out different things, but you can just have a completely phenomenological model where you have these just 2 parameters, essentially quantifying how stable it is, governed by gamma, and epsilon, which is say how much of it goes into the daughter, how much of the energy goes. So you have the original cold dark matter, and then there's a fraction of it which decays. So that is rho 0, and there's rho 1 and rho 2 are the this is the radiation, and this is the non-relativistic species. So what you see is that this is what happens to your Hubble. You see the original dark matter has decayed. So this is I have just shown it because I multiplied with a cube, because a cube is the standard behavior. So just to show how it departs from lambda CDM. So it has decayed, and you see these 2 new species are born. So the adding all these 3 will give you the total density of matter, and this will, as you can see clearly, change your Hubble expansion, depending on what parameters you have. So this is the red one is lambda CDM, and you have different models, and these are error bars from galaxy surveys, etc. Now, importantly, so the takeaway lesson here is when you have dark matter models which are decaying or interacting or have lifetimes, you should first think that there are 2 essential manifestations of it. The first manifestation would be on the expansion history through these different decays. So you can see the Hubble changes. So that is one direct implications of decaying dark matter, because the different constituents have different time evolutions. However, the moment a stable dark matter decays, well, you don't call it stable anymore, it's a decaying dark matter, it decays into a species which is warm. This is a relativistic, it's a fluid, it's like a photon, and this is like something like a warm dark matter. It has some velocity dispersion. The moment you have these species which now has pressure, for example, this thing has pressure now. You can see it has some velocity dispersion. So this is like the sound, it's like if you saw for baryons, the sound speed. This has some speed, velocity dispersion. So the moment you have a species which has velocity like this, what it would try to do is it will free stream through the density field, and it would ease out, it will sort of smooth out fluctuations. So the moment you have decaying dark matter, or dark matter which is having a component or something which is warm, which is no longer stable, and it's not, or at least there's a non-cold species, there's some thermal dispersion of velocities, what it will give rise to is this kind of situation. So you will see there will be decay of the transfer. So the transfer function would have, so this is lambda CDM is divided by, so you see for as you have higher and higher epsilon values, you get more and more decay. So this will imprint, obviously, as you can see in your 21 centimeter or any tracer power spectrum as a suppression of power. So the lesson here is that all these, this whole class of models which has dark matter, which has a warm component, which has a free streaming length, there will be suppression of small scale power for modes which are greater than K freeze. Now, what determines the value of this K free streaming? That is, it's determined by, so I'll just go. So this epsilon, what is this role of this epsilon? It's telling you how much rest mass is going into energy, okay? So this epsilon will actually tell you how much velocity does this warm dark matter, this decayed daughter component gets, and therefore it will set the scale over which, the distance up to which things will be smoothed. So the epsilon determines this free streaming scale, and this gamma, which is the decay time, remember there was this gamma, that the time, that has a slightly different impact. So the value of gamma is actually the time, if it's very early, for example, if the decay is very quick, then what would happen is there would be a lot of these warm dark matters produced, and therefore a lot of warm dark matter produced means there was a significant suppression. So the amount of suppression is proportional to how many such warm particles are born, and that will be dictated by gamma, whereas epsilon, again going to this picture, this epsilon over here, which is the fraction of energy which is gone into the daughter, which tell you how much energetic the daughter is, and that will tell you the scale over which perturbations will be eased. So, I'm just telling you very broadly about the key takeaways of a very large categories of these kind of models. So this kind of transfer functions you will see encounter in different scenarios, which are very different as regards their specifics are concerned, but has the same kind of effect. So I'll just quickly summarize. So what we have demonstrated, I think in a very compact way, is that this post-generation signal is a tracer, and therefore has the potential to obviously probe cosmology at high redshifts. I didn't talk about much of these observational things, but of course it's quite an utopia because of these challenges, but you can do dark energy modeling, different kinds of dark energy model, but idea would be to minimize this modeling details into finally a very small set of observables with which you can sort of limit your observations, and that's what we have done. And similarly for dark matter. So that's about it.
Thanks.